So I hope my screen is visible and I'm audible. Learn one of the most useful data structures in competitive programming along with some other algorithms. So today we will learn about DSU. We will learn about minimum spanning tree, Prince algorithm, Kruskal algorithm, and so on. Okay. So let us start with disjoint union find. Now, whenever you hear problems involving connected components, grouping of objects, any dynamic connectivity, or Kruskal's algorithm in minimum spanning tree, which we will learn in this lecture only, network connections, then there is a very high chance that DSU is the intended solution. Okay, so by the end of this class, you will know that what is DSU, why we need it, how it works, how to optimize it, and how to implement it. So let's begin with simple problem. Here in the PPT, you get the pictorial representations as well as implementations, but I'll be explaining you the concept on the whiteboard. So let us take an example that there are 7 students. Okay. Now these 7 students do not know each other initially. No one knows each other. Now suppose at or every operation, I tell you that a friendship happens. Suppose 1 and 2 became friends. Then in the next step, 2 and 3 became. So now 1 and 2 are friends, 2 and 3 are friends. Then 4 and 5 becomes friend. So 6 becomes a friend. Okay, so 6 and 7 becomes a friend. And then what happens? I tell that 5 and 6 becomes a friend. So these two combine and it becomes like this. So at the end, this is the friendship where this one and this is the friend circle two. Fine. Now, if I ask you that are 3 and 1 in the same friend circle, you'll tell yes. About 4 and 7, same friend circle. If I ask you about 2 and 5, then we will tell that no, they are not in the same. Now imagine that you are given 1 lakh students initially, then 1 lakh friendship operations, and in the middle of those friendship operations, 1 lakh times I ask you by giving friends that are they from the same friend circle or not. Now, in such a case, if for every build the entire connected components using BFS and DFS, it becomes very slow. We need a structure, a type of data structure, which can answer me action and answer another question. Merge two groups. It can merge two friend groups. And another work is tell whether belong to the friend group. Now, these two exact operations that DSU, disjoint set union, this data structure helps us to. Hence, as I told you, it is also known as union find. Why this name comes from? This union is from this step that it can do union of two groups, and find is for this step that it can find if two people are from the same group or not. So one thing that is we need to learn a core idea of this problem. Okay, so let us consider another example. Okay, Suppose I have five peoples. Now, when I tell you that connect one and two, that one and two become friends, I need to tell that who is the leader of that friend circle. Every friend circle should have a leader. So let take, we can choose an arbitrary leader. Okay. So let me choose now let us connect 2 and 3. When we have connected 2 and 3, though to 2, still we have to remember circle that 3 belongs to, the leader of that circle will be 1. Okay. So can you notice something? That we are not concerned about how this entire structure, even this could look like this, and it will mean exactly the same. See, 2 and 3 are in the same friend circle, and 1 is the leader of that friend circle. Here also, 2 and 3 are in the same friend circle, and 1 is the leader of that friend circle. That means every group is actually represented by a leader. Now, we do not need any information how it is connected within the data structure. So, what we need to remember, if there are two elements, element 1 and element 2, and they have the same leader, if they have the same leader, that means they belong to the same group. If they have different leaders, that means they are from the different group. It's as simple as that. That means our DSU operations. As I told you, let us see what are those two operations. One is the find operation. What does this do? This gives in return to me who is your leader. I send find of x, this function will answer to me who is the leader of the friend circle. Okay, that means in this case, the example that we took, if I give a find of 3, then my answer will be 1. Even in this case also, find of 3 will be 1. Okay. Now you will ask me, what does union function do? That union x comma y. What this does is, if xy belongs to the same group, then do nothing. If they do not belong to the same group, then merge their groups together. Now, for example, suppose we have 4 groups. 1 connected, 5 connected. Now I tell you, do a union between 2 and 5. Then what I'll do, suppose this is the leader of this group and 4 is the leader of this group. Then what I'll do is merge the entire thing together. Now it is my choice. I can keep 5 as the leader of the entire group, or I can keep 1 as the leader of the entire group. Both will mean the same. So let me consider that 1 I'll keep as the leader. That is why 1 I'm keeping as the leader. Okay. Now you see, all of these 4 belong to the same group. And if I do find of 5, I'll get 1, find of 4 will be 1, find of 2 will be 1, and find of 1 will be obviously 1. But when they were not merged, find of 5 would return 4 and find of 2 would return 1. And they are from different groups. They are from different groups. Okay. Now, how do we store this? For that, we use an array. Okay. We use an array known as the array stores the values. Suppose initially parent of 1 will be 1, parent of 3 will be 3, and so on. Why? Initially, one is involved in any group. Everyone is individual and they are singly there. If they are any group, that means they are their own parents. There is no leader. Leader until I join a friend group. Same is the case here. Now, whenever join 1 and 2, that time, suppose I initially 1 and 2 were there, now I join and bring them in the same group. That means what I'll do, I'll make of 2 as 1. Now what happens, that parent of 1 is also 1, parent of 2 is also 1. That means they are from the same group. And this parent only leader here that we were talking about. Now, how do we do operation? That find operation goes like, suppose we have the connection, this connection we took. Here, let me tell you what will be the parent, how the parent array will look like. The parent array will look like this. Parent of 1 will be 1. Let me erase this for clarity. Parent of 2 will be 1. Of 4 will be 2. And parent of 5 will be 4. Now, the moment you call this function the 5, what will happen? It will go. Who is the parent 5? 4. Who is your parent? Who is the parent of 2? So go to 2 and ask who is your parent. Who is the parent of 2? 1 is the parent of 2. So go to ask who is he. Now we go to 1 and we ask 1 who is your parent? Replies that self I'm the parent. That means that this is the leader of the group and find of 1, which means whenever we find that the value is the value itself in the find function, that means that is the leader of the group at that moment. We need to remember this because we will use it a lot during the implementation. Now, this is the naive approach. I've shown you the find one also. I have shown you union one also. How we'll do union, we'll do find. Now, okay, let me show, write it once. How we will do the union one. Suppose I am given union of x and y. Then what are the actions that I'll do? First, I will do find of x, px. Okay, you might be confused if I write like, let me do it like this, that px of x, parent of y, py is find of y, px is same as py, then do nothing because they are already in the same group. We do not need to do any union. Else, if they are not in the, I'll do, I will make that parent of x the parent of y. Okay, as simple as that. Once this implementation of union is completed. But this is and why this approach can cause problem. Suppose we are taking our that fine old example that they are our seven friends initially do not know each other. At first, one and two becomes friend. Okay, three becomes friend. Then three and four. Then four and five. Then five and six. Seven. Now you see what it forms is known as a tree. And these are really, really cities. Why? Now, if someone tells me find the parent of seven, I need to go 7 steps up to and find who is the parent or the leader. That means, in the worst case, this find operation will cost me an O of n time complexity. We want to reduce this height. This tree is such a big problem because of this height. Now, can we reduce the height? Yes, we can reduce the height. Now, before going to reduce the height, let me just show you that how the implementation. I'll show it in a very short time. See, parent. Okay. I wish I could copy this and maybe paste here. Let me see if it is possible. No, it's not getting pasted. Okay, let me explain from here. See, it is the make set. This just makes the parent of something. It's only that the initial state. There is nothing to worry about this function. Set function. This is our find function. Okay. If I myself am my parent, then I'll return that yes, this is the leader. I am my parent itself. Else, what I'll do, I will call that find set of my parent. That you are telling me to find the parent of seven. I'm telling you find the parent of my parent. If my parent is six, you go and find the parent of six. That will be your leader. This recursion continues, and finally it gives the output of the. And what is this one? The union function. See, as I have told, A is find A. That is, I am finding the parent of A. I am finding the parent of B. Their parents are not equal. That means belong to the same group. Then the parent of B becomes A. As simple as that. Fine. Now we come to path compression. This path compression. This is a very interesting optimization, and it is like one of the magical optimizations here. Okay, let me suppose in case of path optimization, what happens is that for the first query that you run to find seven, that take O of n for sure. All but of seven is done. Your tree will become very. Why? See, what happens is through this path, I I reach this position, which is actually the leader. I already know that for all the people that for all the students that I have traveled along the way, all of these has parent as one. Then why to keep it in such a straight line thing? How will I make it? Three, four, five, six. I'll connect all of these people directly to their leader. Now, once I have called this find out 7 and my this O of n equation has run, instead can be sure that after this, any asks to find 7, it will be an because all I need to return is parent of 7, and that is 1. That means, what did we do? This long path that we had, we compressed this path to a shorter one. Hence, this is now you can ask, how do we implement this? It might look very hard, but no, this is just one line change in the code. This is a one word change in the code. And how do we do that? We are calling it recursively that go and find who my parent is. So once your parent is found, you instantly put it as the value of your parent so that next time you do not need to call it repeatedly. Instantly have who is your parent. That is why what we do is we set functions same, just cells I initialize before returning. That's it. And this simple modification of the operation, it achieves a time complexity of O of n per call on average. And this is a humongous optimization that we are doing. Okay. The next one is union by size. This is a very simple. What it tells? It tells always join a smaller to a bigger tree. Never a. Now you might ask, why? What is the problem to do that? The problem is that suppose, let us suppose that you have A is of a size 8 and B is a tree of, now see, there is something of size 8, to that you attach something of size increment in height less, but thing of size 2 and you attach something of size 8 below. Always remember, going below that means inserting an extra edge. This makes size more. That is why, like, the increment of size is very less in this case. As the increment of size is very less, so we always remember this, that connect the tree to a bigger tree. So initially we will keep the size of everything as 1. Okay. The size of everything will be, whenever we connect this to this, we will make the size as 2. Okay. So that is one thing. Another thing is the rank, that is union by rank. Same as union by size, just the implementation is a bit different. Is that here also you will follow the same, a smaller rank to a bigger rank. To the rank always by 1 if both the people that you are, their rank is same. If their rank, any one of their rank by 1, and who's the one whom you are considering as the leader. If you are joining two things, I mean two groups, and you consider that the leader of the first group will be the leader of the second group. If they are merged together, then you need to make sure that when they merge, if the rank of both groups are same, of the leader of group 1 should be incremented by 1. Okay. This is the entire concept. The code again is very, very as the normal, like the initial one's code. Okay. How? See, I've given both the codes here, the rank and the size. For size, what you do, time set remains exactly the same. Nothing changes. For union, whose ever you swap and you then initialize the smaller one to the bigger tree, that is a smaller size, you give to the bigger size. And you increment the size of the smaller one. Because now you have increased in size, you are a part of the bigger tree. For rank, what we do, we again do the same swap. For the smaller rank goes to the bigger rank person. But if their rank is same, then you increment the rank of the bigger one, the one who is the leader, increment it by 1. Okay. It is that simple. Now, a very important discussion would be the discussion of time complexity. That in the naive case, both and union is a O of n operation. But then why do we give so much importance of competitive programming and DSA? Because once you combine path optimization with union by size or rank, no matter which one you do, any one would be sufficing. Okay, then we will reach nearly constant time queries. Can you from O of n, you came down to nearly constant time complexity. Like if you do the amortized analysis, you will learn about amortized CS core subjects. That time you will know that becomes O of alpha n. Now, what is this alpha n? It is known as the span function. Now, this function is really a great thing because it grows very, very slowly. So slowly that for any n that is less than 10 to the power 600, like even if you see any code, anything, then at the max you will see that sometimes it is going up to 10 to the power 8. Assume it goes up to 10 to the power 30, the n. Even if that happens, then also this function, when n reaches 10 to the power almost 10 to the power 600, that time this O of alpha of actually becomes O of 4. Okay, so of 4, that means it is so because of this amortized analysis, we need to remember that this is one of the things to implement whenever you remember this implementation very well. In case of competitive, might have a template DSU written, but if you sit for interviews anywhere and you have DSU, then you need to do this implementation on your own at that time. So you cannot use a template. Remember this implementation, it is very easy, it is conceptually also very easy. To Shubham, he will start with minimum spanning tree and its algorithms. And you will also come to know that one of the algorithms in minimum spanning tree, Kruskal. correct implementation of DSU itself. Okay, so passing on to Shubham. I hope you don't have any doubts. If you have doubts, you can ask.
Audible. And my screen is visual as well. You know, the like second part will be looking into the application of minimum spanning tree. So let's start with what is minimum spanning tree, right? So let me go to the board. The weighted connected graph, and it is undirected and it is weighted graph. You can assume any type of graph, and all edges will associated with some weight. Right now, what if I ask you to find what is the total cost of traversing all the nodes? So you might be calculate by using like going from A to B and to C, and you will be simply giving all the weights. But what is the minimum total sum of the weights? So minimum spanning tree help us to calculate that weights across all the edges. So that is about MST. And as in the word itself, it is a tree. So it will have P minus V will be the total number of edges. So it will total of C minus 1 edges. So after uh, converting it into MST, it will look like this. MST can be, but it will have P edges, right? Because in this case, there are four nodes. So converting it into MST, it will look like it will have total number of three edges. Yeah, and then as it is a tree, so it will cycle, and the sum of all edges will be the minimum amount. All the is the tree. Be converting a graph and the minimum total sum. So there are basically there are two terms. First is crystals, and seeing the we have one more algorithm that is Prim's algorithm, right? And the pixel one is basically based on which you have already learned in the part. So let's move on to the implementation of the. So suppose this is a graph, right? Let me take a pencil. Algorithm is simple. Uh, the first part will be we need to make a pair like this, which first part will be right. The second part will be our source. If I am moving from one to two, the source node will be one. So we'll be having like and destination. In this case, it is 2. So I am assigning it as a V. So first we will be converting all the graphs into like this here, right? Then the second step is we will be sorting on ascending order. It is a default method. So we'll be sorting it. So it is here that our the weight will be sorted in ascending order, right? And the third part will be we will have some operation. So we'll be looking to in some time. So first, I am writing this graph as a this form, right? So you can clearly see. So the first, suppose I sorted it in my mind. So the first one will be the clearly see one is the minimum weight. So after sorting, we will have and the source node will be one and destination node will be four. Right? Uh, if I go to the second, which is after sorting, so it will be uh, so I'm writing the source node of three that is sorry first right. So that is three and two eight. And the after three we'll have four, right? Node is three and the destination node is five. Yeah, you can use either of the nodes as a source node or destination node. We can write five and three as well, which is undirected graph, right? So after four we'll have five. So I'm writing there's five. Source node is one and destination node is two. After five we'll have seven. Seven. Then source node and destination node is three. Eight. Then two. Sorry, eight, two, and five. And the order is simple. We are storing weight, then our destination. So on the now we store the elements like this and sort it. Now we'll be having some operation. So operation will be simple. Uh, in DSU part, you have already covered what is find the meaning of leader like this. So we'll from the first one. The first part is weight, the second part is U, and third is speed. So we'll be checking if our U and V same component or same component. So there is no point of change, right? But in you already know that in starting yes, the all nodes itself only. So there are five nodes. So one ultimate parents, or you can say leader, is one only initially, right? Two leader will be the self only like this. So if we take the first one and check the leader of one, it is one only, and for four it is four only like this, right? So it is to uh, say unite the component and like starting it means we need to uh, add that eight also to our tree. So suppose our cost is initialized with zero. So if our component same, sorry, if our both nodes belong from same component, then we'll be adding that. If not, we'll be adding that weight to our cost, and we'll be adding in DSU, like using the unite function, union function, or right. So if I will show you the implementation part, it will be more clear. So I take a vector, and this is a adjacency list. So one second. This is team server, right? There is a find function which will be using for finding the leader, function for uniting it, right? So I am taking a vector, and the pair is like I already explained. The first part will be the weight. The second, first one is source node and destination node. Then after pushing all the elements inside that container, we'll be sorting it out, right? Then so after sorting it out, uh, we'll be going to each of the, can say, elements of that edges ED1, and checking. So we'll be going to edges. Like I am using for loop here for uh, traversing all the elements of ED. Right. The first is weight U and V, and we are checking if like find function using for checking finding the leader of that node. Right. If both leader are different, then we'll be adding that cost to our answer. Good company. Otherwise, if both are from the same company, there is no need of adding that, right? So this is the implementation, and if I, it is not but you have already seen. So the complexity is 4 alpha types. So it's close to e-logging. So you can assume it as a e-log, and space is e plus v. Here e is the edge, the total number of nodes. Sorry, not edge, and e is the edge of total number of edges, right? And v is the total number of. So this is the space and complexity for this approach. Now we have another algorithm for solving the same problem, and this is the Prince algorithm. And in this algorithm, we take a we take a mean heap. As you already know, mean what is the function of mean heap? It prioritize the minimum element at the top, and when we it will be the minimum among all the elements, right? And static queue, we are storing elements. So our first part will be the weight, because second part will be nodes. So I hope in this there is no requirement of one nodes only, because we'll be using BFS travels. So approach for this one is we're starting with any node. Suppose since we are starting with node 1 or root node, and in starting our cost is 0. We already know it, right? So we'll that pair thing in our criteria, and in starting priority is empty. So after inserting it inside, so it will have one element. So it will be at the top. Now we'll be doing is this is the node part. Suppose the graph look like this. This is node one. This is right, and as also we require a visited array also, like we used in normal BFS, right? So we'll have a visited array, which helps us to check whether the node is already visited or not. So when we are inserting it inside, right, and we'll take that node and go to its all adjacent nodes, right? So you can clearly see the one is 2, 3, and 4. So uh, that that is done using PFS levels. You will know it. So we'll be doing is helping moving to its all adjacent. Like this adjacent is the adjacency list which we are storing our all graph component, and we going to all its nodes. Its adjacent node will be checking if it is already visited or not. Suppose if it is already visited, then there is no point of going to that node, right? So next one, if it is not visited, so who is not visited yet? So we can go to node 2, right? So when we are to node 2, will be we have to push all the elements inside our priority queue, which can be traversed, right? But visited, so we'll be pushing all elements. After after coming to this, we'll have a priority queue like this: left 2, 0, and node 3, 0, right? And node 4, 0. We'll do the same thing when our this person will end, and we'll get the total cost. So if I show you the implementation, it will be first. Let's see the what is the question. Question in the question we have given with the first part is P and W. So first we need to convert it into adjacency list. It is given in adjacency matrix format. That's why we are taking a vector adjacent this type, and node and width, right? And we are constructing like the graph is back. Then we are taking a priority queue, and in priority queue, the first one will be the weights because we want to prioritize, and the will be prioritizing the minimum cost. Also, we are taking a visited array, tracking all the nodes if it is visited or not, and we are doing the BFS tab also. So the top part, the first element, and top part and is no. And after accessing the top part, we are removing it. Right? And if it is already visited, so we'll be skipping that. There's no forward. If it is not, and adding that weight, that the excess node weight to our sum, and then from that node going to its all adjacent. And while going to its all adjacent node, if all adjacent node is not listed, then we'll be pushing it our back. If it is already listed, there is no need to push it inside our particle. So this is the dim algorithm approach. Talk about the time complexity. So in the BFS traversal, we already know complexity. L is the total number of edges, and G is the total number of, or you can say, uh, here. So we'll require log phi complexity because may happen that all the nodes, or you can say vertices inside our priority queue. So the complexity of priority queue is a maximum size of the priority queue that can be made. So time complexity will be the E plus V into log V. Space will be the similar as DFS traversal because we are using a vector in the visited one, and one stack memory is also used. That is why we are using O E plus. I hope it is clear. In the second part, we have seen the MST, what is MST, and what are its properties. Then we also see what are the two algorithms which is used to calculate some. Like first one was Pascal and second one was Teams. Right. So this is all about today's lecture. You can ask. Otherwise, you can.